We're going to take a look at the existence uniqueness theorem for first order different initial value problems. And we're going to look at a couple of different examples. The theorem is a theorem for an initial value problem, meaning we need to have a differential equation and an initial condition in order to use this theorem. And what we want to look at is this function here, the right-hand side of our differential equation, which we call f. And we want to know, is f at our initial point here is 0, 0, is f continuous at 0, 0, and is the derivative of f with respect to y, which in this case is t over 2 times the square root of y, is that continuous at 0, 0? And the answer is no, right? This is a problem. This is not continuous at y equals 0 because we have the y in the denominator, and that function does not exist at y equals 0. So this initial value problem does not satisfy the requirements of the existence uniqueness theorem, and therefore we have no guarantee that a solution exists, and we have no guarantee, if a solution exists, that it is unique. We don't have any guarantees because we don't pass the conditions of the theorem. It's fairly straightforward to check. We need to look at the function and its derivative. The derivative here, remember, we got that through looking at the square root of y as y to the 1/2, and then using the power rule on that. So let's look at this one. Right here we have the function. And the point we're looking at is 1, 5, and the function is fine at 1, 5. There's no problem with this function, so f is fine, no problem there. But the derivative of f with respect to y we also need to look at. That derivative looks like 1 over t minus y squared times minus 1 from the chain rule. That is also fine at 1, 5. No problem there. All right, so the function and its derivative are both fine at this point. And so we have a guaranteed, I can't spell guarantee, guarantee of existence and uniqueness. There is, that's existence, there is a unique, that's uniqueness. There is only one solution to this differential equation in the neighborhood of this initial condition. Don't know how long that's going to last, but at least for some neighborhood around t equals 1, we're good. Now I want to just very quickly look at a slight modification here. What if we had initial condition of y of 2 equals 2? Right, if we have y of 2 equals 2, we're looking at the point t equals 2, y equals 2, then the denominator here would be 0, right? So when we look at f at 2, 2, we would be looking at 1 over 2 minus 2, 1 over 0. This function is not continuous at 2, 2. So we would not meet the conditions. We'd have no guarantee. And the point of me saying this is just to point out that the initial condition is part of the problem. It's not just the differential equation that we're looking at, it's the combination of the differential equation and the initial condition that we need to look at here.